All right, we're going to take a look at the Wile E. Coyote problem. It says a 20-kilogram Wile E. Coyote is shot out of a cannon straight up with an initial velocity of 50 meters per second. They want us to analyze this in two different ways. One way where we say some energy is being converted to thermal, and some way where we say that we're not having an energy converted to thermal. And we're going to ask, with no thermal energy loss, what's the maximum height they would reach above the cannon? And then figure out what if 20% of the kinetic energy is converted to thermal, then what's the maximum height? So take a look at this. I'm going to start first with a sketch of the situation. So say we have our cannon here. All right. Let's see here. All right. And the barrel of the cannon. We got that directed upward. All right. And we're going to launch the coyote, who I'm just going to represent as a box. He's going to get launched up the barrel of that cannon. Right, and then up into the air to some final position here, right? Let's see here. We know that the mass of Wile E. Coyote, they tell us that his mass is 20 kilograms, and which would be heavy for a coyote, I think. And they tell us that his initial velocity is 50 meters per second. So that initial velocity of 50 meters per second, I think the intention is that's the velocity as he leaves the barrel, okay? That's the intention, okay? By initial velocity, I think that's what they mean, because he's going to start at rest here in the cannon. So I think when he gets here, the velocity is going to be 50 meters per second. Right. Okay, so here's what I'm thinking. They want us to do LOL diagrams for 4 positions at rest in the cannon. So this would be like position A. As he's just leaving the barrel of the cannon, position B. Then it says halfway up to his maximum height. Now, of course, you're like, well, what do you mean maximum height? Do you mean maximum height above the starting position A or maximum height above the end of the barrel? I'm going to say halfway up from A, okay? So on my diagram, that's hard to see, but it's probably somewhere like here. We'll just say it's there. Say that's halfway to his maximum height. I'm going to run off the top of the page. Sorry, I should have drawn it lower. And then D at his maximum height, okay? Okay, so not a great sketch, but I think that's the idea. And I think the idea is that when he's here at B, that the V at B is 50 meters per second. I think that is the intention, okay? And that C is at half the max height measured above A. So I'm going to right away, I'm going to go ahead and mark. I'm going to call here at A. I'm going to say the height at A is 0. And then this is at half height, half max height. Okay, there we go. All right. Okay. All right, good enough. Okay, so having been given that, they say do 2 different sets of LOL diagrams. One for if we are saying there's no energy loss due to thermal. So here we go, A, B, C, D. I'm just going to do it here. A, B, C, D. And then we'll do one with thermal energy loss. A, B, C, MD. All right. A, B, C. Okay, so one of the things I have to decide is what my system is going to be. Certainly, I'm going to have the coyote being part of my system. And then you say, well, in deciding what else we're going to include, we got to think about what outside forces are acting, what objects are interacting with them to see whether we want to include them. Pretty much, I am assuming that there is some compressed air, perhaps, that's firing him up here. Okay. I mean, I suppose they're typically in a Coyote and Roadrunner cartoon, there's some sort of gunpowder that's going to explode and push him up. So there'll be some external force pushing him as he goes from A to B, say expanding gases. Do I want to include that gas in the system? If I do, then I'd have to deal with that chemical reaction happening to the materials in my system. I don't want to do that. I don't want to have to do that. I want that to be some outside force pushing me from A to B. So I'm gonna say that. So I don't want to include that force. I don't want to include the gunpowder as my system, or that expanding gas in my system. I want that to be an outside thing doing work. You say the only thing. Let's see here. Is he going to be in contact with the barrel of the cannon? You're like, we're going to say there's no thermal energy loss, so we're going to be ignoring friction with the cannon walls. For the first one, we'll probably put that in for the second one, though. And then there's just the only other thing in acting then, really, if we're ignoring that, there's the gases pushing him up and then just the earth pulling down on him. So I'm going to include the earth so that I can do a gravitational potential energy term. I'd rather use UG if I have the option. So Coyote and Earth is going to be my system all the way across. Coyote and Earth. Coyote and Earth. All right. Okay. So from A to B, there is an outside force acting, and that is that force from the expanding gases. It'll be pushing him up in the direction of motion, making him go faster and faster. So it'll be putting work into the system, work from the expanding gases. All right. But once he leaves that barrel, that's expanding gases are going to kind of spread out. They're not going to be pushing him up anymore. So the only outside force then is the gravitational force, but that's not outside because we're including the Earth. So there's no other work terms for the other ones. So this is what the transfer diagrams look like for the other two. No energy going in or out. All right. Types of energy to include. Are we going to include kinetic? You say yes because that's changing. Kinetic, all the way across. We're going to include universal gravitational potential energy. Yeah, because Earth's part of the system. We can have that, and we are changing heights all throughout. So I'm going to include UG. Are we going to have any elastic energy? You say no, we don't have anything getting crushed or expanded. The gases are, but they're not part of our system. Then you have chemical. You say it's chemical reaction with the gunpowder and stuff, but again, that's not part of our system, so we don't have to worry about it. And then thermal, we are ignoring thermal in this first case. All right, so this is what that looks like. We're just going to be looking at these two energy types. Is there anywhere where we know the kinetic energy is 0? And you'd say, well, it's 0 here, and then the gases push it up, and when it gets to B, it's going at 50 meters per second. So at the start here, 0, and then at the maximum height, the speed is going to be 0 at the max height. That's where we would stop to run and start falling back down. The speed is 0 there. Gravitational potential energy, what we're going to call gravitational potential energy 0. We decided to call height at A 0. So the potential energy here is 0. That's kind of cool. All right, and that's it. So taking a look at this, the total energy should start at 0, but we know that by the time he gets to position B, he's going ridiculously fast, 50 meters per second. So he's got a lot of kinetic energy there. How much kinetic energy do you want to say he has? I don't know, 10 units? How much gravitational potential energy do you want to say he has? Well, he's at some height above here. Okay, we weren't really told how long the cannon barrel is, so I don't really have any numbers or values for this. I don't know. I'm just going to say it's 2. All right. Now look, here the energy was 0. Here the total energy is 12. So the work done by the expanding gas, must be 12. All right. Okay, going from B to C. The only force acting is gravity, but that's inside the system between Coyote and Earth, so there's no energy transfer. So the total energy here must also be 12. I'm at half the height of the maximum height. Okay, now this is going to be weird. Do I know anything about the max height? Well, I know that, look, there's no other energy transfer along. So the total energy here has got to be 12, and the total energy here is 12. But at this point, there's no kinetic, so the potential must be 12. If I'm at half that max height here, I'd be at 6 units of potential. Do you see that? Okay, saying that C is at halfway to D. It doesn't look that way. Sorry, I ran out of space, but that's the idea. So the kinetic here must be, well, again, the total is 12. If we got 6 in potential, it must be 6 in kinetic. And that is my LOL diagrams for no thermal energy transfer. I'm going to use this to answer the next part of the problem. What's the max height above the cannon he could reach with no energy transfer? And then I'll come back and do the other ones with thermal energy. Okay, and I'll do this diagram, then do those. Okay, so I'm going to hold off on this. Let's do the calculation for part B. What's the maximum height above the cannon he could reach if we are looking at it with no thermal? And so you say, well, we're going to do energy calculation. I don't really know, because I don't know. Oh, okay, so notice what they're asking. Sorry, the way they phrase it is the height above the cannon, right? So like above the cannon barrel. So they're really just asking for how high I am above here. This bit is what they're actually going to ask for in that part. So what do you want to call the length of the barrel? Me too. Let's call this L. Okay, and this height here above the end of the cannon, let's call that, I'm just going to call that D, that distance above. Okay, okay, and that's what I'm trying to find in this part of the problem. Okay, so here we go. We're going to go from B to D in this analysis. Okay, I'm going to go from B to D using the work energy theorem. Because we have Earth in the system, we're going to have gravitational potential energy also, right? Okay, outside forces doing work. If I did my, now we're going from B to D. The force diagram for the Coyote going from B to D, the only outside force is that gravitational force. But that's not really outside the system. So it's not a work term. So that's a big 0 for work. Delta K at D, that's the maximum height. We know the speed at the max height is 0. And so the kinetic energy at D minus the kinetic energy at B, right? Let's see what the kinetic energy at D is going to be 0. I'm getting ahead of myself here, but that's okay. Delta UG, that'll be the UG at D minus the UG at B. Right? Neither of those is going to be 0. They're both above the 0 line. All right. So if I cover this up, we say that's the work energy theorem showing only the non-zero terms. 0, kinetic energy at B, potential energy at D, and gravitational potential energy at B. Here we go. Let's put in our equations and figure out what this is going to look like. Negative 1/2 mass speed at B squared plus mass G height at D minus mg height at B. Okay. This is going to be a little tricky here. One thing you might notice, if you wanted to at this point, is that there's a mass in every term. So I could cancel all those m's. Bam, bam, bam. Okay, I'm going to move this minus 1/2 v squared to the other side. I'm going to move my work up here. On the other side now I have g height at D minus g height at B. Okay, now here's the thing. These heights they didn't give us. Okay, what we're really trying to find here is how high above the barrel we are. So my height at D that total height above the 0 position is L plus D. Do you see that? So this is going to be G times L plus D minus G. The height at B, that's just L. Do you see that? Well, if I go ahead and I'm just going to go distribute the G's. You'll say, look, this is GL plus GD minus GL. GL and minus GL, they're going to cancel each other, right? They just shoot, shoot. And look, I got rid of that L, which is good because I didn't know how long the barrel was. And the only variable now is D that I don't know. And that's what I'm trying to find. So that actually worked out really, really nicely for me. Oh my gosh, look at this. This was a negative, and I moved to the other side. It should switch and become positive. Sorry about that. 1/2 VB squared, then it's just going to be G times D. Divide through by G. What have I got? I got VB squared over 2, and I divide by G. That gives me D. Let's put the values in. The velocity at B we know is 50. And when I punch that in my calculator, I'm going to get 50 squared divided by 19.6. And I get 127.55 meters. Ta-da! All right, not too bad. This was a little trick here, assigning variable names to these things, okay, to find just this amount. All right, say that our heights are at L plus D and at L. Okay, so that's that part. Okay, last part. They say, first of all, they say list 2 possible ways energy could be transferred and converted to thermal. I would say thermal energy conversion comes from, we've said, friction and collisions, and technically from radiative energy, like absorbing energy from sunlight or something could increase your thermal energy. You say in this one, I would say one way is through friction with the walls of the cannon. Maybe as he goes up, he's kind of bouncing around a little bit, kind of scraping along, right? Maybe it's a tight fit. So friction and bouncing around, rubbing on the walls of the cannon. I could also think about, if you want like air resistance, he's going to be pushing air ahead of him out of the cannon barrel, right? Speeding up that air, making the air swirl around more as he goes up. Air will be kind of having to push out of his way. It's like he's having little collisions with air molecules. If you wanted to worry about air resistance, it might really start to matter in confined spaces where the air can't get out of his way very well. He really would be starting to push some air ahead of him significantly there. So that would be where we'd get some thermal energy, perhaps, from those ways. All right, so we want to do LOL diagram now, considering that some energy gets converted to thermal. So what is that going to look like now? And you'd say, well, if some energy is converted to thermal, let's see. We're saying that's going to happen because of maybe friction or interaction with the air molecules as you bump into them. So I'm going to still choose to make my system just be Coyote and Earth. Okay, so C and D. All right. And I'm still going to be looking at kinetic and gravitational potential energy. But I'm going to choose to represent that thermal energy as energy that's exiting the system, heating up the air, heating up the barrel of the cannon as he rubs against it. I know some of it would heat the Coyote too, and if we could put like a euthermal term here too, specifically for the Coyote getting heated up, some of that thermal going to Coyote. But what we're told in the last part is that 20% of the kinetic energy had at the end of the cannon was transferred into thermal. What's the maximum height he'd reach now? So it's going to be easier for me to just consider that energy as like out of the system. If it's heating up the Coyote, that doesn't help him get higher. So it's as if that energy was just removed for purposes of our calculation. Is that okay? So I'm not going to show a thermal energy here. I'm just going to say that's the energy that was taken out of the system by that friction force and air resistance force. So I'm just going to say that as he's going up the barrel here, he's going to lose some energy. And this is work that gets converted to thermal. It's kind of like work from friction and work from like pushing the air ahead of him out of the barrel from that resistive force. Okay, and that's going to be happening from A to B. Once he leaves the barrel, he's not going to be pushing this huge amount of air ahead of him. It will tend to kind of get out of his way. There will be some air resistance, but it won't be as significant as in the barrel of the cannon, I don't think. And there won't be that friction with the barrel. So I'm just going to diagram it as that energy loss is happening between A and B. If all of this with thermal seems a little hand-wavy to you, that's okay. It feels that way to me too. We're having to make some simplifications to make this problem solvable, basically. Okay, we're kind of making some approximations here, simplifying assumptions. Alrighty, what's this going to look like now? Well, again, if I still do the same thing, same starting height being there, and starting kinetic energy being 0, starting from rest there at the bottom of the cannon, this is still 0 and 0. Okay, the difference, and I still have that force from the expanding gas behind it. We'll say we're still going to pump in, say, 12 units of energy. Actually, you know what? No, that's okay. If I'd been thinking, I would have made this something that was divisible by 5. But oh well. Well, it's my problem. No, we'll keep it like this. Yeah. Now, in going from here to here, if we said 12 units were put in, we ended up with 12 units of kinetic and gravitational potential when we got to the end of the barrel, right? But this time, we're going to lose some now because of friction and air resistance here. So we're not going to end up with the full 10 here, right? Now, peeking ahead, they tell us that 20% of the kinetic energy is transferred to thermal. 20%, that's a fifth. That doesn't go into this. The point I want to make is I still have the same height at the end of the barrel here as I had in this case. So that's still 2. But I won't have as much kinetic, right? Now they tell me 20% of the kinetic at the end of the cannon was transferred to thermal. So I'm going to say I only have 80% of the kinetic I had there. So instead of 10, I only have 8. So 20% of the 10 is 2. That's the energy that was removed like that. Okay. Right, and then as I go along, again, if I'm halfway up to my maximum height, now to my new maximum height. What's my maximum height going to be? Well, all this, no energy transfer now. The kinetic here is all going to get converted to gravitational, so I'll have 10 units of gravitational potential energy at the end now, and none in kinetic when I'm at the peak. Halfway of that max height, so it won't be at C, it'll be a little bit lower than it was before. You know what I mean? This is now a new C location. You want to look at that? Halfway of the new max height, or do you want halfway of the old max height? How do you want to treat this? I'm treating it as the new half of the new max height. Is that okay? Then instead of being 10, this is going to be 5. All right, instead of 12 and 6, 10 and 5. I'm not losing energy from B to C, so the total energy was 10, so this is also 5. All right, so that's the way I'm looking at that. If you wanted this to be actually the same position here, it would have to have the same gravitational potential. This would still be 6, but now this would be 4, right? If you want to do it that way, that might be a nicer way of doing it. So at the same position I was at before, I'm going to be going slower. And so this final position, I'll never actually make it to that original position D. This will have to be a little lower than D. Is where I hit that max height now. My new max height is going to be lower. All right. So what do they want us to find here? They want us to find what that new max height will be if 20% of the kinetic energy at B was converted to thermal. So here we go. Here's how I'm going to set that up. So we didn't have the full kinetic energy. We only had 80% of the kinetic energy we had originally there. So the speed is not going to be 50 at the end of the barrel. It's going to be slower. I'm going to do my calculation from B to D just like I did before. And look, going from there to there, we're not losing any energy, right? So the calculation is going to look exactly the same. The only difference is this value for kinetic energy at B is only going to be, if we lost 20% to thermal, it's only going to be 80% of the value we had here. So what I'm going to do is I'm going to do the same thing. Same thing. And you'll see the one little modification we're going to do. All right. So I'm still going to go from B to D. I'm still going to do sigma W is delta K plus delta U G. I'm still going to say, hey, we have kinetic energy at D minus kinetic energy at B plus UG at D minus UG at B. We're still going to say, hey, at the peak, the speed is 0. So that drops, right? But we're going to say we only have 80% of the kinetic energy as we had here. So I could use these values, but then I have to just multiply, take 80% of it. So I'm going to multiply by 80%. That's 0.80, right? So I'm just going to multiply this by 0.8. That's 80%. Okay, and then do my calculation, all right, with 80% of the kinetic to start with. That's it. That's all I'm going to do. So I'm going to run through the same calculation. Everything will look the same. Should I write it all out? Sure, I'll write it out very quickly. All right, so minus, now this 0.8 factor, right? The UG minus UB, I'm just going to skip ahead. MG height at D, the height at D we're calling L plus D. Minus the height at B, mg times L, the length of the barrel. Okay. Again, this mgl and this minus mgl will cancel each other out. So I'm just going to get mgd. Okay. And I'll have this minus 0.8 times 1/2 mvb squared. Okay. When I'm going to transfer this up to here because I'm running out of space because I was trying to do too much stuff on one piece of paper. All right. When I transfer that up there, okay, what's this going to look like? Is it okay if, first of all, sorry, this is equal to 0, right? Do you notice that there's an m in every term? Yes, so the m drops out just like it did before, right? So you cancel that m, junk, junk, right? All right, and so putting this in, negative 0.8, putting in my values, 1/2 VB squared. Now again, this isn't the actual speed at VB. It's actually going slower than 50, but that's what that 0.8 factor is for fixing that. We're not going 80% of the speed, we're going 80% of the kinetic energy, okay? So don't do 0.8 times V and then square that 0.8. That would be just 0.64 times the original energy, that's not right. Okay, plus 9.8 times D. Okay, and that D is what we're trying to solve for. So I can do the math. If I move this term to the other side, the sign would flip from negative to positive. Life would be good. So here we go. I'm going to have 0.8. I'm going to move to the other side, it'll be positive 0.8 times 1/2 times 50 squared. And I got to divide by 9.8. Dang, I keep pressing the wrong thing. 0.8 times 0.5 times 50 squared divided by 9.8. There we go. So I get 102.04, 102 meters per D. And you say, no, wait. So you say, hey, look, so that is less than the height we had before. We didn't have that 20% energy loss.